Okay, please flip to 7.2 in your notebook. You have a picture at the top there of a couple of gentlemen trying to figure out the height of a tree by using the shadows of the tree and of a meter stick. So the students in this picture are using a meter stick and shadows to measure the height of the tree. How could they do this?
The height of the tree and the stick and the length of the shadows are going to be proportionate to each other.
Ah, nice. So the height of the tree is going to be proportional to the length of the meter stick. The shadow of the tree is going to be proportional to the shadow of the meter stick. And we don't really care about the hypotenuse in this situation other than it represents the direct line of sunlight hitting each of them. And the sun is so far away that the difference in position from the tree and the meter stick is negligible, okay? Because that sun is really far away. So that's not going to make any noticeable difference. But that's a good strategy. So that's what they're going to do. They measure the length of the tree's shadow. They determine that it is 8 meters long. The shadow made by the meter stick is 1.6 meters long. What does that give them? Well, Mr. V, when you relate two lengths to each other and they have the same units, then we call that a ratio. Good. But that's the only information that they're given, or is it? Is there other information in this diagram that I haven't written down? How about the length of the meter stick is 1 meter? Okay. So we're going to complete this out for them really quickly and then move on to our notes. What are we saying? We've got corresponding side lengths. Does that make sense? The shadows are corresponding to each other because they're proportional in these similar triangles. I know that they're similar because they're both right angles. That's the first thing that we're going to end up proving, that the true triangles in question actually are similar. Okay? And we know that the angle that the sun hits makes with the top of the figure is going to be equal because the sun is so far away again that the distance between these things is negligible. It's going to hit those at nearly exactly the same angle. And then we know that our third angle then is also going to be equal in each triangle. Okay, so we've confirmed that they are actually similar triangles, which tells us that side lengths correspond to one another, which tells us that there is a proportional relationship between corresponding side lengths. Now, we're going for the height of the tree. So out of the 3 side lengths that come out of corresponding triangles, okay, similar triangles, we're going to create 2 ratios and we're going to set them equal to each other. We know from last lesson that the relationship between 8 and 1.6 is the same as the relationship between t and 1. So the same thing that multiplies us to get from 1.6 to 8 is going to multiply to get us from 1 to t, the same factor. That's what our notes are going to be on in a little second. Okay, how do I solve this? T over 1 is just t. Multiply both sides by 1.6. That'll eliminate my 1.6 over here. That'll give me 1.6t. 1.6t equals 8. Divide both sides by 1.6. Anybody got a calculator out?
5.
So 8 divided by 1.6 is 5. And this is measured in meters. So we know the height of the tree is 5 meters. All they had was a meter stick and a measuring tape. Okay, all they had was a meter stick and a measuring tape, and they determined the height of that tree fairly accurately. Okay, so let's look down. That's basically what we're working on today, is stuff like that. That's kind of example 1. It wasn't actually example 1, but that's what we're working on. So let's go to our notes. You've got a notes section, and in that notes section, we're going to talk about something called a scale factor. Scale factor. You're going to do a little comma, and then you're going to do a cursive K. What does that mean? It means that when we're talking about a scale factor, we're going to use the letter K to represent that scale factor. Okay? And when you see the letter K, K equals something, you know they're talking about the scale factor in this unit. Okay? So what do we know about it? Well, this is a factor, or the factor. The factor that relates lengths, that relates corresponding side lengths. That relates corresponding side lengths of two similar triangles. The scale factor, or sometimes we'll say scalar factor, is the factor that relates corresponding side lengths of two similar triangles. You have a little bit of a diagram down below. You have triangle ABC and triangle PQR. And there is a scalar factor that allows us to go from the side length in the smaller triangle to its corresponding side length in the bigger triangle. Do you know what that scalar factor is?
3.
It's going to be 3, okay? So in the diagram, K equals 3, which means we could take any side length from the small triangle, multiply it by 3, and get any side length in the bigger, get the corresponding side length in the bigger triangle. How would I go from the bigger triangle to the smaller triangle? I'd multiply by 1/3. Okay, I'd multiply by 1/3, or I would divide by 3 to get the corresponding side length in the smaller triangle. Does that make sense to you guys so far?
Yes.
Okay, so let's fill in the box there, the little chart. You have the first box is going to say triangle, ABC, side lengths. The next box is going to tell us what to do. We're going to multiply by K, our scalar factor, and that's going to give us our triangle PQR side lengths, the corresponding side lengths. All right. So let's take our first side length in triangle ABC. Let's just say AB. What's the length of AB?
2.
AB equals 2. We're going to multiply that by our scalar factor. What's our scalar factor?
3.
And that's going to give us, therefore, the corresponding side in PQR, which is PQ, equals 6. Okay? Let's do it again with BC. BC in our little triangle is 4. Do we multiply that by the same scalar factor? Yep. That's what it means when things are proportional. 4 times 3 is, therefore side length QR is 12. Go ahead and fill in the last line on your own. You can call it AC or CA. Whatever you call the first one, make sure your corresponding line segment, that the letter order actually corresponds to the letter order you used in the first place. So we can apply the scale factor to find an unknown side length in one triangle if we know the corresponding side length in the other triangle. Okay? Another thing I can say, so what did that mean? That means if I know my scalar factor is 3 and I know any of these side lengths, I can automatically get the corresponding side lengths. The other thing that we can do is we can create the scalar factor. Anytime we know corresponding side lengths from two different similar triangles, we can find that scalar factor. We can find the ratio and apply it to our other corresponding side lengths. So that's exactly what we're going to get into in example 1. In example 1, you have a diagram. It shows a river, and it shows some information that you can gather just from being on one side of the river. So this person is going to get an approximate width of the river just by standing on one side of the river and marking some things, or identifying and looking across and seeing some things, okay? So here we go. To determine the width of the river, Naomi finds a willow tree and a maple tree directly across from each other on the river. So we've got a willow on the far side, and we got a maple on her side. Then she's going to use a third tree on the tree line, on the river line, and that's a sumac tree. So we'll use S. She's going to plant 2 stakes there, and she plants a stake at B. Move it out of my way. B. And she's going to stand at 90 degrees to the river. And she's going to stand at A, it sounds like. Or just plant another stake there. So your diagram looks something like this. And we are going to find the width of the river using the information that Naomi found. Now, we can find the length of the river if and only if these things are similar triangles. So my first step is to confirm whether or not they are similar triangles. Okay? How do I do that?
20, 45 by 3.9.
2 right angles.
Yeah, step 1. Show that triangle ABS is similar to triangle WBM. Okay, that's my first step. I need to demonstrate that, or else I can't use this scalar factor. Okay, so I first need to show that they are similar, that the side lengths are corresponding. So how are we going to do that? You wanted to start with, we actually don't know. We know that the maple is at 90 degrees. We actually didn't tell us yet that S is 90 degrees, but it did tell us that these lines are parallel to each other. Okay, so you can only use what the diagram gives you. So the one thing that we know really simply here is what? We know that B is opposite. They're opposite angles, so they're going to be equal. Okay, so here's our first statement. We've got a statement over here, and we've got a reason over here. Our first statement is that angle ABS is equal to angle WBM. ABS is equal to WBM. How do I know? Opposite angles are equal. Opposite angles are equal. All right, that's helpful. Now, what else do we know? What else do we know?
That 9.3.
No, we're talking about angles. We need to show that the triangles are similar, so we need one more set of equal angles.
S and M.
How do we know that S and M are equal?
Because they are the same thing and they have right triangles instead.
We do not know that this is a right triangle.
Oh.
Okay?
But it's
In
the same.
7.0, we learned what happens when you have two parallel lines and a transversal.
It makes right.
They're supplementary.
Okay? Not supplementary. We're looking at angle S and angle M. They're not complementary either. They're going to be equal. They're going to be equal. Okay? And the point there is that they are alternate angles. Okay? So we've got angle.
Yeah, Sienna heard me. I was saying that.
Good job. I can't afford another mistake though, can I? Okay, we've got BSA and BMW. They are both
BMW.
90 degrees because alternate angles are equal. Yeah, it's an expensive angle, eh? The BMW. It's flashy. And because of interior angles add up to 180, we know the third angle is going to be equal, so we don't even need to write that. Now we just simply need to confirm our statement. Therefore, triangle ABS is similar to triangle WBM. And how do we know? 2 pairs of corresponding angles are equal. All right. Now that we know for sure that they are similar, what can we do using this information?
We can correspond and see how big the triangle is and say that they're similar. So,
What was that?
We're going to find the scale factor, okay? Step 2, we're going to find the scale factor. What does that mean? That means that K is going to be our scale factor. That's going to be the number that we can multiply any side length from the little triangle to get the corresponding side length in the big triangle. So we actually need corresponding side lengths that we already know about in order to create the scalar K. Are there corresponding side lengths that we know? We know that BM corresponds to SB, so we know that 24 relates to 9.3 by this scalar factor. So we know that the scalar factor is 24 over 9.3. That ratio will hold true for the relationship between any of the corresponding side lengths in the similar triangles. Okay? Now, what are we trying to find out? What are we trying to find out?
if they are corresponding.
No, we know that they're corresponding. We're trying to find the width of the river. So we're trying to find WM. Which side length from the little triangle does WM correspond with?
AS.
SA 8.4. Okay? So we know that this scalar factor, this relationship between these side lengths is the exact same as the relationship between these side lengths. Okay? So this is our scalar factor. I'm not going to divide that out. Not going to simplify it at all. Okay? Don't need to simplify it. That is my scalar factor. I've got decimals here, and this doesn't easily simplify. It'll just be more decimals. So I'm going to leave it like that because I want the exact value. So step 3, and maybe I'll move this over here. Step 3, find width of river. Again, I know I'm looking for WM. You said that WM corresponds to SA or AS. That means that they're going to have the same ratio as BM over SB. Okay? So now I know. I'm going to plug in what I know. I don't know WM, so I'm going to leave that in my numerator. I know AS. AS is 8.4. And I know K. What's K? 24 over 9.3. Now I have a proportion. I'm looking for the width of the river. What do I need to do to get the length WM? Multiply the left side by 8.4. If I do it to the left side, I have to do it to the right side. On the left side, I'm just going to be left with WM. And on the right side, I can put this in my calculator a couple different ways. I could go 24 divided by 9.3, hit enter, and then hit the multiplication. That'll go answer times 8.4. Or I could do 24 times 8.4 divided by 9.3. Okay, whichever way you end up punching it in, you should get approximately 21.667. Now, am I going to leave that as my final answer?
Nope.
No, it's kind of too precise. It's rounded, but it's to the nearest thousandth, which is a bit much because all of my other answers are only to the nearest tenth. So I'm going to take this answer and I'm going to give it a final answer. And because she's just kind of standing on the river putting stakes down and guessing at angles. Okay, this isn't like a perfect science. Anyway, what we're going to end up with is the width of the river is approximately 22 meters. The width of the river is approximately 22 meters. That's pretty reasonable for her guesstimation. Thanks, Naomi. Way to go. Step 1, demonstrate that they are similar. Demonstrate that they are similar. Sometimes if I give you an assignment or a homework problem, it will say these triangles are similar. Then do you have to do this step?
No.
No. Okay, but if it doesn't say that, you need to show that based on what's in the diagram. Now, for saying that S and M were equal, I could not say that these are both 90 degrees right away. I had to acknowledge that they are both 90 degrees because they are alternate angles. And I got that from these parallel markings. So pay attention to your diagrams, pay attention to the markings that you have. You'll basically always have the same angle. That'll be one of them. They're equal because they're the same, okay, or they're opposite or something like that. Then you find the scale factor using corresponding side lengths, which allows you to solve the rest of the problem. Then let's head into example 2, areas of similar figures. So it's going to be a similar concept, but we're going to see how area is different from working with side lengths. So here we go. It's almost a little bit of thinking and investigation. Here we've got the relationship between the areas in each pair of similar figures. What is the relationship? So here we have a little triangle. It's a 3, 4, 5 right angle triangle. Then you've got this bigger triangle, which is a 6, 8, 10 right angle triangle. And we're asked to find the area of each and then compare them, basically. So we're looking at the similar triangles. So we've got the smaller triangle here. How do I find the area of a triangle again? Area equals 1/2 base times height. Okay? In a right angle triangle, it's pretty easy. Height is the altitude, which is given to us. It's 4. The base is 3. So we have here in the small triangle 1/2 times 3 times 4. 3 times 4 is
12,
half of that.
6.
All right, so we've got 6 square units. 6 square units here. And then for our larger triangle, we're going to use the same. This is the area of the small. This is the area of the large triangle. We're going to use the same strategy. It's a right angle triangle, so I've got 1/2 times 6 times 8. 6 times 8 is 48. Cut it in half. 24 square units. So what's the relationship between the area of the small triangle and the area of the large triangle? Yeah, the area of the small triangle is 1/4, or we could say the area of the large triangle is 4 times greater. Area large is 4 times greater than A sub S, the area of the small triangle. And we're going to do the same thing with our rectangles. We've got a rectangle here with side lengths of 2 and 3. We've got a larger rectangle with side lengths 8 and 12. What's the area of a rectangle?
Right times width.
Area equals length times width, LW. All right, area of small rectangle is 2 times 3 equals 6. Area of large triangle, 8 times 12 equals 96. Okay, now let's try to figure out the relationship between AS and AL. Should probably have your calculator out unless you're good with mental math.
Oh, yeah. It's clearly
12.
no,
No, 16.
Yeah, 16.
Okay, 6 times 16 is 96. 6 times 16 is 96. Okay, so that's a bit of an investigation. We're going to leave that idea on your notes. I'm going to have to erase. But basically you're seeing that, I mean, we can kind of do it in our heads. And B says, what's the scale factor? Maybe I'll just do it off to the side for a second. So section B asks us to get the scale factor that will allow us to multiply for side lengths from side length of the small triangle to the corresponding side length in the larger triangle. So how would I find that? K equals, well, I take two corresponding sides and I just put the bigger one over top of the smaller one. So for the triangles, the similar triangles, the scale factor is 2. Right? I take any side length in the little triangle, multiply it by 2, I get the corresponding side length in the big triangle. Okay? Let's do that same thing down here. Again, this probably isn't the best way to organize your notes, but I'm just doing it so that allows me to keep it all on the board at the same time. And this one still isn't really on the board, so I'm going to bring it down here. So for our similar rectangles, yeah, so what's our scale factor for our rectangles? What do I have to multiply to get from my little shape to my big shape? Yeah, I got to multiply by 4, right? 8 over 2 or 12 over 3. And now in C, we're comparing our answers from our regular side length scale factor and comparing that in each case to how much bigger the area is. And you're right, it's going to be k squared each time. If you have the area of the little triangle, right, which is 2 times 3 is 6 in here. This is rectangles. And I multiply it by k squared, then I'm going to get the area of the larger triangle. Why is that? Well, I'm going to just quickly use this picture. I'm just going to quickly use this picture to draw what we had. So we've got something that looks like this. This is the little triangle, little rectangle, okay? This is side length 2, side length 3. And what we're doing when we're using the scale factor of 4 is both dimensions are getting multiplied by 4. Well, we said area is length times width. So if the length gets multiplied by 4 and the width gets multiplied by 4, we're actually multiplying our original area by 2 factors of 4, by k squared. We're going to have 4 extras here, and 4 times this length, and we're going to have 4 times this length. So it's getting multiplied by 4 twice, k squared. Okay? Does that make sense to you guys? Same thing happens in the triangle. One of the dimensions, the base, got multiplied by 2 from 3 to 6, and the height got multiplied by 2 from 4 to 8. So inside the addition from here to here, the change is that there's going to be 2 more factors of 2 here. This got multiplied by 2, and this got multiplied by 2. Okay? So to get the area from the smaller triangle to the larger triangle, or the smaller figure to the larger figure, we're going to multiply by our scalar factor squared. Okay, I'm going to write that as a little note on the bottom of this example. So just to wrap up this example before we go to our specific note, we can say for C, in both cases, the ratio of, let's just say, let's use our symbols, A sub L, the ratio of the area of the larger figure to A sub S, the area of the smaller figure, is equal to the square, well, let's just say is equal to k squared. Is equal to k squared. Mr. V, can you translate that for me? Yep. All we did was take the ratio AL over AS, the area of the larger figure over the area of the smaller figure, and that came out as k squared. And that's in contrast to when we did side lengths, right? The side length of the smaller figure over the side length of the larger figure is k. That's how we find out our scalar factor. If you do it with areas, you end up with k squared, which means that for side length, you can go smaller times k equals larger side length. For area, you can go smaller times, these are backwards. For area, you can go smaller times k squared equals larger, or larger divided by k squared equals smaller, okay? Okay, so a final little note on that so that you can see that it works for every single pair of similar figures. Basically, all we're going to write, I'm going to do it all in symbols, okay? Yeah, on the same page on the bottom, do you have like some space?
Yeah.
Okay, so I'm going to draw a diagram, and then I'm going to just give you some words that go with it. Now, does it matter if this is not a right triangle?
No.
No, it doesn't matter, okay? It's going to work for any figure. It would work for an octagon.
What about
That'd be harder to find the area. Anyway, let's carry on. And then we have similar triangle here. Again, also not necessarily a right triangle, although my diagram kind of looks like it. So you've got triangle ABC and PQR. And we're going to be told that triangle ABC is similar to triangle PQR. And we're going to write the scalar factor situation a couple of different ways. So what did we learn? Here we learned that if we take the area, if we want to know the area of PQR, that's the larger triangle in this, or the larger figure in this example, we're going to be doing k squared times the area of triangle ABC. Okay? And yes, you do need to be able to understand this type of expression and how this is worded. What else can we say about it? Well, we can say something about k squared. How would we find k squared? Well, k squared is simply the area of PQR over the area of triangle ABC. That equals k squared. So this is a ratio. The ratio as with respect to the area of the larger over the area of the smaller is going to get us k squared. But again, even if you didn't have the area of either, okay, let's just say they only gave you, I don't know, well, let's assume they're right now. Let's not even go into that. Basically, you can get k from side lengths. You can get k squared from area. But you could also get k squared from side lengths, because if you can get k from side lengths, you can get k squared, right? You just square it. Anyway, we'll see some examples as we move along. All right, in example 3, we're solving for an unknown area. So we have a little bit of a map here. You've got 3 streets in a city and a railway, a railroad crossing, railroad, I guess, train track. There we go. The shaded area is going to be an industrial zone. You see that in your image. We're going to find the area of the industrial zone. And we're told that king and queen are parallel to each other. So I'll draw the same diagram that you guys have, ish. Do my best anyway. Looks something like this. Boom. Boom. And we're told that this is parallel to this. We can label some things here. Just give them the same letters I'm giving them. You've got a K in the top left, a G down at the bottom, and we're told that that is 3 kilometers. Just transferring information from our other diagram. Okay, I'm going to put an R there, a Q here, and an N here. Now we'll all know what we're talking about. We're also told that from Q to N is 1 kilometer. Okay, and we're also told that this line
It's perpendicular.
is perpendicular to Queen Street, and it is 1.4 kilometers. Now, why did they give us that line?
Because that also means that King Street is perpendicular to that line.
Yeah, not important. Why did they give us that line?
Just for fun.
It's going to be the altitude of this triangle. It gives us the height of this triangle. Now we have base times height of the smaller triangle. And we know that these are similar triangles. How do we know that? Because our first step is going to be identify similar triangles. So let's make a note of that. Step 1. Identify similar triangles. Identify similar triangles. Who can help with that? First of all, what do we need to identify to know that they're similar?
Angles.
They have to have two sets of equal angles. Two sets of equal angles. Okay? So which angle would you like to start with?
Angle QG and NK.
How about this one right here?
Yeah, that's what
R? Yeah?
Oh,
QRN and GRK. So here we go. We've got our statements on the left. My first statement is going to be angle KRG is equal to angle NRQ. How do I know that they are equal?
because
What's-
they are
Opposite. Good job. Opposite angles. All right, let's take on another one. What other helpful piece of information is in our diagram?
that
The parallel
one, yeah,
lines.
The parallel lines, which means,
That means that G and Q are same angles.
yep, and I can do either of them, right? I could talk about G and Q, or I could talk about K and N. Doesn't really matter because they both have this parallel line with the transversal going across. They're both alternate angles. Okay, let's do
G.
RKG is equal to angle RNQ. And we've already said they are alternate angles. So once if you're in your head, you can see that, but you just don't know what they're called, flip right back to 7.0. You have the names of what they're called right there. Takes you 2 seconds, and then you'll be able to see, because now we have two equal angles, that we know the third one has to be equal because of the sum of interior angles of a triangle. So 2 is enough to say what? That triangle KRG is similar to triangle NRQ. How do we know? The reason: corresponding angles are equal. This is going in the garbage. Later. Okay, so since they're corresponding, we can then identify the scale factor. Okay, we're going to find the scale factor. Step 2, determine scale factor K. Well, how do I do that? Well, I have corresponding side lengths, right? I have the base of each triangle. So all I have to do is identify that K is the ratio of KG and NQ. Okay? It's always good to don't skip this step, okay? Tell me what you're doing. Tell me where your line segments are coming from. Show me that you know that these are corresponding line segments in similar triangles, and that's how you get the scale factor. Okay? Say, oh, Mr. V, we're looking for area. We actually need K squared. Yeah, we'll get there. Okay? We'll get there. So here we go. Here's our scale factor. We've got 3.0 over 1.0, 3 kilometers over 1 kilometer, which reduces to K equals 3. Okay, we're going to keep that off to the side for a second because there's something else I need to determine now. Do I have enough information to get the area of one of the triangles?
Yeah.
Yeah, I do. So now I'm going to be looking at my little triangle. Okay, we'll call it step 3 since we're identifying all these steps. Step 3, get area of, what was it, NRQ. Q. Area of a triangle is 1/2 base times height. So the area of triangle NRQ is 1/2 times 1 times 1.4.
Hopefully it doesn't get area of triangle and
Yep, says it right there.
no, get area.
General. I don't know. You're asking about this?
No,
I think
one,
Okay, 1.4 divided by 2, folks? 0.7. Okay, so the area of this triangle is 0.7 square kilometers. Squared. Okay, last step is to use our scalar factor to determine the area of the industrial zone, that larger triangle. Let's maybe write it. Step 4. No, you don't need to write step 1, step 2, step 3, step 4 when you're doing your own practice problems. Use K to determine area of triangle KRG. We know the relationship. If not, you can flip back to your notes that you just took on the last page. All we need to say is that the area of triangle KRG is equal to K squared times the area of triangle NRQ. I'm running out of real estate. K is 3. I'm going to show every step, so I'm going to make sure I put 3 in for K, and I'm going to still square it, and I know the area of my smaller triangle is 0.7. Alright, so now I have 9 times 0.7, that's just 9 times 7, move the decimal 1, 6.3 kilometers squared. Okay, wrap it up with a final statement. The area of the industrial zone is approximately 6.3 kilometers squared. In this case, they actually gave us exact measurements, but I mean, seems more likely that it's an approximation.
will we get points if we don't say approximately?
Yeah, I wouldn't worry about it. All right, your practice problems come from page 324. That doesn't work.
Maybe you should use the linear field.
Page 324, you're responsible for knowing numbers 5 through 9. Enjoy.